Welcome back to the speed run. There are really 4 big ideas that you need to know for the fluids chapter in AP Physics. I'm going to start with the last one, but maybe it's the most important, which is Bernoulli's equation. In Bernoulli's equation, we think about 2 situations where there's a pressure differential. Let me throw up a couple of examples. Here there's a pipe of water with a height differential. So there's pressure at one point at the beginning of the pipe and pressure at another point later. Bernoulli's equation will allow us to see what the relationship between the pressure in this one is and the pressure in that one is. For this question, we might say if the velocity is the same in both parts of the pipe, that the pressure would be different, exactly like the rho GH part of Bernoulli's equation. Another example of Bernoulli's equation that would be really helpful is if we had a tank of water and the water was still at the top, but there's a hole at the bottom and water is flying out the bottom. And here we would say that the pressure is the same at both sides. This is an important trick. Whenever water is exposed to air, we say that the pressure at that point is going to be the atmospheric pressure rho naught. Whenever the water is exposed to air, we see that the pressure at that point is going to be in equilibriums with the air, which means it will be pressure naught, 1 atmosphere of pressure. That's 100,000 pascals of pressure. So here, for this one, the pressure terms are equal on both sides, and the only difference is there's a height differential, and that's causing the velocity term in the second part. So we could think about the water up here having kind of potential energy, and here it's kind of having kinetic energy. And we derive the equation velocity is square root 2gh. Let's imagine a third situation, and this is also about Bernoulli's equation. So here we're going to have a pipe with one thickness that opens up into another area with a second thickness. So here we need another equation, and we're going to need the flow equation, which is the second important equation you need to know. The flow equation says that the area times velocity at one point in the pipe is the area times velocity in the other part of the pipe. We're saying that the total volume per second here is equal to the total volume per second here. So what's going to happen is in the narrow pipe, it's going to flow faster, and in the larger pipe, it's going to flow slower. And we could calculate what that velocity would be in the second part. So we might rearrange the formula like this. Because the second area is larger, it's going to be a step down from this velocity, so that velocity is going to be slower. So here, if we look at Bernoulli's equation, we would say that the kinetic energy like term here is smaller than the kinetic energy like term here is larger. It's going faster, and here it's going slower. So this part must have a larger pressure to compensate for that by Bernoulli's equation. So with Bernoulli's equation, we can have a pressure difference, we can have a height difference like this that causes pressure differential. Here, pressure is balanced, so the height difference causes a velocity. Here, we have the height is the same for both pipes, the center is the same, but there's a velocity change which causes a pressure change. So Bernoulli's equation is all about this balance, and we threw in the flow formula there too. If you're struggling with FRQs, on my site are a bunch of resources to help you understand FRQs. You can get them for absolutely free. The third key formula that you need to know is the buoyancy formula. The force of buoyancy is rho Vg. We imagine a block of water submerged in a liquid, and we say that the V is the volume of the block, and this block is displacing a volume of water. The rho is the density of the liquid. So the force of buoyancy always points up, and the larger the block is, the more volume of water is displaced, and the larger the buoyancy force upwards will be. When we think about a block in a situation like this, we may want to think about a normal free body diagram, and there could be 2 or even 3 forces happening. So with the force of buoyancy, we're going to include it in our normal Newton's second law kind of thinking. If the force of buoyancy is in balance with the force of gravity, there's going to be no acceleration on this block. Another thing that happens with the force of buoyancy is sometimes the block is partially submerged. So the key idea here is when a block is partially submerged, the volume we put into the buoyancy formula is going to be the amount of volume that's beneath the surface of the water. So not the whole volume of the block, just the amount of water that's being displaced by the block. The final formula you need to know about for fluids is the pressure formula. There's actually two forms of this. There's the gauge pressure one and what we call the absolute pressure one, but they both have the same idea. The idea is that when there's a liquid, what matters is how much height of liquid is above you that causes pressure. Here are two people swimming in a tank of water. One of them is a little bit under the surface and has H1. Pressure is rho GH, so this person will have only a small amount of pressure of water on them. The second person is much deeper in the water with a larger H, so they will have more pressure on them. The difference between the two formulas, the gauge one and the absolute one, is that when we measure with a gauge pressure, it already includes the atmospheric pressure in it. So we just kind of ignore that term, and we normally think of pressure as rho GH. However, there is this thing called atmospheric pressure, and if we want to talk about what the true pressure is, we would say it's the pressure from the water plus the pressure from the atmosphere up there. These are the four key formulas from the fluids chapter that you need to understand.